So the first thing that we're going to do is emphasize a couple of key parts to the Ka and Kb calculations that are going to help you calculate or anything involved with the calculations of Ka and Kb. Because a lot of people get confused because there is a formula that relates them both. So one thing that I want to say is that when you're dealing with Ka is for acids only. Okay, so you should never be calculating Ka for a base because it really describes, okay, the extent to which H plus is released in solution, right? And the thing is about bases is that they don't release H plus. So Ka is for acids only. Same thing with regards to Kb is that this is for bases only, okay? And so it describes how you could say H plus is accepted, so how readily it gets accepted, or it could also describe how OH is released in solution. And so a lot of people get confused when it comes to Kb and Ka because they feel like they're completely interchangeable. You could find a Kb value for an acid and it would be fine. Really, the definitions are not compatible. Ka is the constant for acids only and Kb is for bases only. And the formula that combines them both, which I'll kind of write at the top here, which is the Kw is equal to Ka times Kb. This formula over here is really used for conjugates, right? So used to find conjugates. So let's say if I give you a Ka value, and I say find the Kb, well, that Kb that you're going to find is not for the same substance. That Kb would be for the conjugate of that acid only. And the same thing is true when it comes to if I give you a Kb value. If I give you a Kb value and you find the Ka, all you've really done is find the Ka of the conjugate acid of that base. But it's not the same substance entirely. So Ka is for acids only and Kb is for bases only. The next key part to these problems is using something called the 1000 rule. And what the 1000 rule is it's really just a mathematical tool. So I'm going to write over here, it's just a math tool used to, and this is really, it's hopefully, avoid a quadratic. So what we say is this. So it's called the 1000 rule because if the initial concentration, okay, of the substance, so usually in this case, if it's a Ka, it'll be of the acid, is greater than or equal to 1000 times the Ka value, we can assume that the equilibrium concentration is equal to the initial concentration. We can assume that it essentially fully ionizes. Okay, so the equilibrium concentration is going to be equal to the initial concentration. So whatever concentration we gave you in the problem, that would be equal to the equilibrium concentration that you can plug right into your equilibrium constant. And so the idea behind this is that if the acid concentration is high enough, so we'll say is high enough it'll increase the strength of the acid, and it'll almost fully ionize. And for us, that almost is going to be good enough for us to neglect anything that might be lost. So this is also called, you could say, the 5% rule. So in university, they might call this the 5% rule. And it looks like this. So let's say I give you an acid, we'll call it HA, and we tell you that it's 2.0 moles per liter. What you would do is you would take the 2.0, you would divide it by the K value, the Ka, so we'll write Ka of HA. And all you really care to see if this is going to be greater than 1,000. If it is, if so, and it passes the 1,000 rule, you can neglect the X in the denominator. And I'll just write in denominator. So if it is greater than or equal to 1,000, you can neglect the X in the denominator, which means you're not going to have a quadratic to deal with. Now here's the key application and the usefulness of the 1,000 rule. If your concentration passes the 1,000 rule and you can neglect the X in the denominator, then you get to use the shortcut. So if, we're going to write this here, if 1,000 rule test is passed, okay, then there's no ice table and there's no quadratic, and that's nice. And so what we can then skip to, the shortcut, is if you're trying to find H3O plus, which is your X value, if there's none of these, then you can always jump right to this formula here, which is H3O plus is equal to the Ka value of the acid multiplied by the concentration of the acid. And again, the minute you do the 1,000 rule test and it passes, you can jump right to this. You don't have to do the ice table or any of those kinds of things. Now the same is true for bases as well, except the only thing is, when you're doing the 1,000 rule test for the base, and I'm going to erase this here so that we could see what the formula would look like. If we're going to do the 1,000 rule for the base, then instead of the Ka value being used for the 1,000 rule, we're going to use the Kb. So for bases, you're going to take the concentration given and you divide it by the Kb value, right? And if it's not given, then we can find it using the Kw is equal to Ka times Kb. Okay, and that's how we would do it. That's only if the question doesn't give it to you. If it gives it to you, you don't have to worry about that. So, yeah, the concentration over the Kb, and if that's greater or equal to 1,000, then the shortcut would apply here as well. You don't need a nice table. You don't need a quadratic. The only thing is that the formula looks a little different because remember, bases don't release hydronium, right? They release a substance called hydroxide. So our shortcut would look like this. It'd be OH minus is equal to the Kb multiplied by the concentration given of the base. And I would say that when it comes to these, approximately 90% of questions use these shortcuts. Okay? So before you start solving any of these, always do the 1,000 rule test first. So first off, we're going to take, so for this calculation over here, We're going to go 0.200 moles per liter. We're going to divide it by the Ka that you find in the data booklet for hydrofluoric acid, which in our case is going to be 6.3 times 10 to the negative 4. And again, it's the Ka value right to the left. What you end up seeing is that this has a value of about 317.4. I wrote 14 here, but it should be 17.4. So this fails, so I'm going to write this here agreed. This fails the 1000 test. So the concentration isn't 1,000 times greater than the Ka value. So what that means is two things. This means that one, you need ice table. Okay. The second thing that it means is that you may not, but you may need a quadratic as well. But the first one is a definite. So with these in mind, let's proceed to solve the problem. So the first thing we do here is write a proper Bronsted-Lowry reaction for your acid in question. In this case, it's hydrofluoric acid. It'll react with water. Water will act like the base. Hydrogen is donated to the water from the hydrofluoric acid, leaving us with F- and H3O. The second thing we do is create an ice table. Now, one little correction here that needs to be made is that, remember that water is not included because it is a liquid, so we should write H3O plus. And so the initial concentration given for hydrofluoric acid is 0.2. It loses a mole as we go towards the right, or as we move forward. So it's noted with a negative x, so it's 0.200 minus x. While the rest, as the reaction proceeds forward, gain a mole. So they're plus x, add plus x. And because they're products, they shouldn't exist at the beginning, so they start at 0. And so we have at equilibrium x and x. Next, with the information from our ice table, we create the Ka formula. And when we substitute everything that we know, it looks like. And of course, once we simplify this, we get the following. And then, of course, bring all the terms on one side. We'd cross multiply this. And we would end up with 6.3 times 10 to the negative 4. And then that's 0.200 minus x. And that's equal to x squared. And when we FOIL this completely and bring all of these to the other side, we end up with the following equation. And so we finally get our equation in standard form. If I rewrite this here, that would be negative x squared, minus, so we'll go minus 6.3 times 10 to the negative 4x plus 1.26 times 10 to the negative 4 equals 0. So your negative 1 represents your A. The 6.3 times 10 to the negative 4 represents your B. And here's your y-intercept, or your C value. And so what we could do is to find our exact values of x, we could use a discriminant and just go x is equal to negative b plus or minus b squared minus 4ac over 2a. And we know what the A, B's, and C's are, so we could just substitute them in. This plus or minus just means that you're going to do the calculation twice, so one with the plus sign and one with the minus sign. And so substituting everything in, we end up getting 6.3 times 10 to the negative 4 plus and minus, and then of course that's going to be 6.3 times 10 to the negative 4 squared minus 4. And then A is a negative 1. And C is negative 1.26 times 10 to the negative 4 all of this gets divided by 2 multiplied by -1. And when we plug those into our calculators, we get two values. X1 is equal to a negative 0.01154, and X2 is equal to 0.01091. And so we have two X values. They both can't be right, or they can't both be right. This one would lead to a negative concentration. If we go to the ice table, for hydronium and the fluorine or the fluoride ion. So this wouldn't work. So this is the one that we're going to accept. And so then to find the pH, we would take that concentration, because remember that X is really equal to our H3O plus. So with that in mind, we would go back here. We could erase this bottom over here and just go pH is equal to negative log 0.01901. And when we plug that into our calculator, we end up getting a value of about 1.96, and that's the pH of this. So when the 1000 rule doesn't work, it becomes a much longer. Now, if we look at the other one to compare the 2 moles per liter hydrofluoric acid, well, the first thing that we're going to do, if we want to find the pH of this one, we're going to do the 1000 rule test, and hopefully we don't have to do another quadratic again, because that was not too fun. So we go the concentration over the Ka value in the data booklet, which is really equal to 2.0 moles per liter over, okay, the Ka value, which was 6.3 times 10 to the negative 4. It's the same acid, so it wouldn't be different. And this time we get a value of 3,174. The main point is that that's greater than 1000. So the 1000 rule passes. And so if the 1000 rule passes, that means that there's no ice table or quadratic. So we could jump right to the shortcut, which is going to be H3O plus is equal to the root of Ka multiplied by the concentration. The Ka value is 6.3 times 10 to the negative 4, multiplied by the concentration of 2.0 moles per liter. And that'll be our H3O plus concentration. When you plug that into the calculator, you get the following. So our H3O plus ends up being about 0.0354. And when we plug that in to the pH formula here, we end up getting a pH of about 1.45. Okay, which makes sense. The more you increase in concentration, the lower the pH goes for the acid. So this one was nice, and I would say that majority of questions are like these.